In this lecture, I will talk about the design of shell and tube heat exchanger. And before going into the details of the design of shell and tube heat exchanger, I'll talk about the basic components of shell and tube heat exchanger and the layout of the different types of tubes and the baffles and the inner components of shell and tube heat exchanger. So the next is, let's talk about the shell and tube heat exchanger. So these shell and tube heat exchangers are known as the versatile type of heat exchangers, and the shell and tube heat exchangers has numerous applications, and it can be used in the industries such as for the power plants and the wastewater treatment and in the process industries. So it has vast applications across the industries. So they are also used in the air conditioning and the refrigeration systems. So I will give you a few examples related to the shell and tube heat exchanger and their applications in the air conditioning and the refrigeration systems. So the next is, let's talk about the basic components of shell and tube heat exchangers. So we are going to discuss the shell and tube heat exchangers and its design. So before going into the detailed analysis of the shell and tube heat exchanger design, we must have idea about the basic components of shell and tube heat exchanger. So this is a kind of a labeled diagram of shell and tube heat exchanger. So it has various components, and you must go through each and every part of the shell and tube heat exchanger in order to get the idea that the particular components of shell and tube heat exchanger, right? So the basic components are, I'll just explain briefly that it has a front head and the rear head, and it has a shell which has a specific type, and it has baffles, and it has tubes, and tubes have different layouts, and the arrangement of the tubes and the tube layout, such as in the type of pitch that I will explain in the upcoming slide, has a great influence on the heat transfer coefficient as well as the pressure drop calculations. So I will explain that in the upcoming slide, that different kinds of the tube layouts and the different shell types in the upcoming slide. So go through it. These are the 39 components that is being labeled in this shell and tube heat exchanger. So the next is the shell types. So the shells in the shell and tube heat exchangers are basically classified with specific names, right? So the front end and the stationary head types, and the rear end the head types. So there is the front head and as well as the rear head, as well as the shell types depending upon the flow directions, right? Or the pass or the flow directions, flow configuration in the shell side. So each head type, either it is the front head or the rear head, has been specifically associated with a specific number. So such as like the one pass shell, which is represented by E, right? And the two pass shell with longitudinal baffle, which is represented by F, and the split flow, which is represented by G, right? So this is basically classification of the front head and the rear head with the shell types depending upon the flow directions, and it is associated with the different nomenclature. So you must go through the nomenclature of different shell types. The next is depending upon the flow dimensions, like the flow direction, which is one pass shell, and it is represented by E, right? As you can see in the previous slide. So one pass shell, it means that the fluid which basically enters into the shell will complete only one pass, right? So it is represented by E. And here you can see that the fluid which is entering into the shell will complete only one pass from this end to this end, right? So this is the fluid which is entering from this point and leaving at this point. This is known as the one pass shell. Similarly, this is the shell type which has the two pass shell with the longitudinal baffle, and this is a horizontal baffle which basically diverts the flow, right? So the fluid enters from this point and it will flow from this point to this point. It will complete one pass, and this longitudinal baffle will direct the flow in another direction, in the reverse direction at the bottom side, and the fluid will move from this point to this point and will leave out from this point. And this, in this way, from this point to this point, the fluid will complete the second pass. And similarly, the split flow, the double split flow, and the cross flow, and the cross flow, combined flow for the condenser, and these are the different flow categorization for the different shells, and it has been associated with the different names, and the specific nomenclature is being used for the different shell categories. So this is basically classified by the TEMA. So TEMA is actually an association which is stands for the Tubular Exchanger Manufacturers Association, and all these classifications are basically given by this TEMA association. After going through the classifications of the different kinds of shells, let's have a look on the tube bundle types and the shell and tube heat exchanger. So as you can see that this is the tubes. These are the tubes which is inside the shell. So the tubes are basically actually the U tubes, right? So it is it has a shape of U, so that's why these are known as U tubes. So this is known as the bundle of U tubes, right? So the fluid enters from here and it will complete one pass in the U tube, and this will complete the second pass, right, in the tube bundles. So these tube bundles sometimes have extra surfaces on its outer side. So this is the shell and tube heat exchanger type, in which the tubes are bare tubes. Let me just see you in the next slide. So a bare U tube, baffled single pass shell and tube heat exchanger, right? So this is the bare U tube single pass shell and tube heat exchanger, right? Single pass means the fluid enters into the shell side from this side and leaves from this side, right? So similarly, this is the second kind of heat exchanger, in which we can see that this is the bundle of tubes, right? And the tube bundles have extra surfaces, or the extended surfaces, or the fins on the outer side of the tubes, as you can see in this shell and tube heat exchanger. So these extra surfaces or the fins on the outer side of the tubes will actually used to enhance the heat transfer coefficient, or will actually to increase the heat transfer coefficient that is being used for the design of the heat exchanger. So I will show you in the upcoming slide, or when we see the design example of the shell and tube heat exchanger, we'll see that whether we have to use the bare tubes or we have to use the fin tubes, and it is basically depends upon the fluids that we are basically using in the particular operation. So the next category is a kind of shell and tube heat exchanger. It is a 2-tube pass baffled single pass shell and tube heat exchanger designed for the mechanical cleaning for inside of the tubes. So these are the 3 tubes, 1, 2, 3, right? Let's take an example. The fluid is entering into this compartment, into the front head, and the liquid will flow in these 3 tubes, 1, 2, 3, right? And it will pass through these 3 tubes, and it will come here into this head, right? And then the fluid, after coming from these 3 tubes, will enter into these 3 tubes which are on the lower side, right? And again the fluid will move from left to right into this compartment, and then it will leave out from this point. So this is a kind of fluid which is basically moving inside the tube, right? And the shell side fluid will actually enter from here, and it will complete one pass and leave from here. So this is a kind of heat exchanger which has two pass tubes that is basically used, where we are using the fluid inside the tubes which is basically a dirty fluid. So if we need a frequent cleaning, so we have to use this kind of heat exchanger. So if we are using the dirty fluid, we need to clean our heat exchanger, or the inside of the tubes of the heat exchanger needs the frequent cleaning. What we do is we remove the front head and remove the rear head, and after that we can just easily clean the tubes which is inside the shell and tube heat exchanger. So if we have the U tubes, so the U tubes are difficult to clean as compared to the straight tubes in the shell and tube heat exchanger. So this is a kind of another heat exchanger which has basically a floating head. So floating head means the floating head has the capacity to move to and fro because of the thermal expansion of the tubes and the shell. So sometimes we have to use the fluid in the heat exchanger that is very hot, or that has a very high temperature, or as a result of very high temperature there might be the small expansion in the tubes as well as in the shell. So that expansion can be accommodated by using the floating head type heat exchanger in the design of heat exchanger. Next, let's talk about the tubes and tube passes. Generally, a large number of tubes passes are used to increase the tube side fluid velocity as well as the heat transfer coefficient within the available pressure drop, and to minimize the fouling, right? So the tube metal is very important, so we have to be very selective, and we have to select a particular material that is being used for the tube design in the shell and tube heat exchanger. The tube material may be the low carbon steel and the low alloy steel, stainless steel and the copper, and that has many materials are available from which we can use to prepare the tubes in the shell and tube heat exchanger. The one thing is that is very important, that the material that we have to use will ultimately cause less corrosion or less fouling in the shell and tube heat exchanger. So the wall thickness of the heat exchanger of the tubes is standardized in terms of the BWG of the tube, that is the standard which is known as the Birmingham wire gauge. So you will see this terminology when you see the design example of the shell and tube heat exchanger. So the next is the small tube diameters. If we have the small tube diameters from 8 to 15 millimeters, and which is basically preferred for the greater ratio of area to volume density. But for the cleaning purposes, we have to use up to 20 millimeters of the tube diameters, right? And in the millimeter in diameters. For inches, it could be 3 by 4 inches. So larger the tube diameters are often required for the condensers and the boilers. So if the tubes are very small, so it is very difficult to clean the tubes from inside, right? And if the tube diameter is large, so it would be easy to clean the tubes from the inside. So sometimes in the operations we have used the liquid which is basically results the scaling or the settling of unwanted materials on the inner side of the tubes, and that ultimately sometimes cause the fouling. And you have seen in the previous lectures that the fouling results in the smaller passage of the fluid inside the tube. So that's why we have to use the tubes that is basically easier for the cleaning purposes. If we use the larger diameter in tubes, so that would be easy for the cleaning purposes. So the next is the tubes may be either bare or have very low fins on the outer side. So I have already explained this, that the tubes may be the bare tubes or have the extended surfaces on the outside. So low fins tubes are basically used when the fluid on the outside of the tubes has substantially very low heat transfer coefficient than that of the fluid which is inside the tube. So the fluid which is outside of the tubes, which is basically in the shell side. So there are two fluids. You have already seen that in one of the design examples of the double pipe heat exchanger. The one is the inner pipe tube and the one fluid which is the annular fluid, right? So in this case, the one fluid would be the tube side fluid, right, and the one fluid will be the shell side fluid. So if the shell side fluid has a very low heat transfer coefficient, so we have to increase the heat transfer coefficient, and we will use the tubes which will have the extended surfaces on the outside of the tubes, so that will increase the heat transfer coefficient. So the tube length is very important. That will affect the cost and the operation of the heat exchanger, right? Basically, if we use the longer tubes, so what we will have to use, we will have to use the fewer tubes or the less number of tubes in the design of the heat exchanger, so which will ultimately be a favorable point for us, and it will have the fewer holes we need to be drilled in the sheet that is basically used in the shell and tube heat exchanger, and the shell diameter would be decreased if we use the long tubes. If we use the long tubes, so obviously we have to use the small number of tubes, and ultimately shell diameter will also decreases. If we use the smaller tubes length, if we use the tubes which are in smaller length, so what we will see that the number of tubes will increases and the shell diameter will also increases. If the shell diameter increases, obviously the size of the shell and tube heat exchanger will also increases, and ultimately the cost will also rise. So if we use this configuration that is being given in the third point, then ultimately we will be in the lower side of the cost. So the next is the tube layout. Tube layout is basically characterized by the included angles between the tubes. So after going through this slide, I will show you the next slide, which is which will show you the different configurations of the tube layout. So a layout of 30 degree results in the greatest tube density and is therefore used, and unless other requirements dictate otherwise. So it depends upon the requirement whether you have to use the 30 degrees, 45 degrees and the 60 degrees. I will show you. And for example, the clear lanes that should be 1/4 inch or 7 millimeter are required because of the external cleaning, which is basically preferred with the 90 degree or the 45 degree layout. So the clear lanes means the distance between the tubes in the shell and tube heat exchanger. This is sometimes known as clearance, and it is represented by C. And this why I am emphasizing on this point, because you have to use this clearance in the design of the shell and tube heat exchanger. The layout is also very important. So the next point is the pitch. The tube pitch, which is represented by PT, is usually chosen so that the pitch ratio should be the pitch divided by the outer diameter of the tube is usually in between 1.25 to 1.5, right? I will show you the next slide about the tube layout. So when the tubes are too close, the tube sheet becomes structurally weak. So what is the tube sheet? So let me give you one example. If we have the bundle of tubes and the tubes are basically fixed in the shell and tube heat exchanger. So the how we can fix the tubes? So we will do the welding of the tube with the tube sheet, right? So that it will become fixed in the shell and tube heat exchanger. So if the tubes are very close, so the tube sheet becomes structurally very weak because of the large number of holes inside the tube sheet. So the tube layout and the tube locations have been standardized. So there are different configurations that we will see in the design of the shell and tube heat exchanger. The number of tubes, which is simply known as the tube counts, that can be placed within the shell depends upon the tube layout, tube outside diameter, pitch size and the number of passes and the shell diameter. So pay attention on these different terminologies, that the tube layout, right? So I have also explained the tube layout, which either it could be 30 degree, 45 degree, 60 degree or 90 degree layout, and the tube outside diameter, and the tube pitch. Tube pitch means the distance between one center of the tube to another center of the tube, which is known as the tube pitch. I will show you in one of the upcoming slides. So the number of passes of the tubes and the shell diameter, these are the different design parameters, which is very important when you design a particular shell and tube heat exchanger. So this is an example that, for example, consider we have the 1 inch outer diameter tubes layout on 1.25 inch square pitch, right? Square pitch means the tubes, the 4 tubes which are arranged in a square manner, right? And the distance from one center to another center of the tube is 1.25 inch, which is known as pitch, with the shell diameter is 31 inch. So this is the one information, that we have the 1 inch tubes and the tube pitch is this and the shell diameter is 31 inch. So the next is, if the tube arrangement is in that one pass, right, which is represented by 1p, so we can have the maximum number of tubes, which is 406. And if we change the configuration from 1 pass to 2 pass, so the number of tubes will be slightly reduced, so it would be approximately 398. So see how the design would be changed if you change the configuration of the shell and tube heat exchanger. So this is a kind of the layout. So these are the 3 tubes, and which are basically arranged in the shell and tube heat exchanger. So this angle will be 30 degree. So this is the triangular pitch, and this is the 45 degree pitch, right? 45 angle, right? And this is the 90 degree, right? And this is the 60 degree layout of the different kinds of the tubes. So there are different configurations, as you can see that in this diagram. Let me just bring one of the next slide that will clear the idea about the pitch and the clearance and the layout as well. So this is basically diagrams which will show you the kind of square pitch. So what does square pitch means? The 4 tubes are arranged in a square manner, right? So we have a square, so each tube has a center at one of the corner at the square, so this is known as square pitch. So triangular pitch means, so if we have a triangle, so each corner of the triangle will be at the center of the one tube. So in the square pitch we will have the 4 tubes in because square will have the 4 corners. In the triangular pitch we have the 3 tubes because we have 3 corners of the triangle. So here the angle would be 90 degree in the square pitch, and in the triangle obviously we know that the angle is 60 degree. So the distance between the tubes, right? So this is one tube, the center, and this is the outer diameter of the one tube. This is the outer diameter, outer side of another tube. So the space between these 2 tubes is known as C, which is known as C dash, or sometimes known as C, which is known as clearance. So the second thing is the pitch, the distance from the center of the one tube to another tube center. So this distance is known as the pitch, right? So there are 3 things that are very important in the tube layout. The one is the pitch type, either it is square pitch or the triangular pitch, and what is the clearance, the distance between the 2 tubes, and the pitch is the distance between the 2 centers of the tubes which are arranged adjacently, right? Let's talk about the baffle types and the geometry. So the baffles basically used in the design of the shell and tube heat exchangers serves the 2 functions, that the most important to support the tubes inside the shell for its structural rigidity, that basically prevents the vibration and the sagging of the tubes, and the second is to divert the flow across the bundles to obtain the higher heat transfer coefficient. The next is the baffles may be classified as the transverse or the longitudinal baffles. For example, the F shell has the longitudinal baffle. As you have seen in one of the previous slides, the transverse baffles may be classified as the plate baffles or the rod baffles. So the longitudinal baffles are basically the baffles which is along the shell axis, right? And the transverse baffles are at the 90 degree of the shell axis. Let me just show you the different kinds of the baffles, and as a result it will result the different kinds of the flow behavior in the shell side. So this is the single segmental baffle, right? So this is the baffle which has a different number of holes, and the tubes are basically passed through these holes, and it will basically be attached with the shell side. So it will serve two purposes. That the first, it will hold the tubes, and second, it will direct the shell side flow inside inside the shell. So the flow direction would be in this way. The shell side fluid will come here, and this baffle will direct the flow in this way, and this baffle will direct the flow in this way. So the baffles are basically used to direct the flow inside the shell. So this is the single segmental baffle, right? So this is another classification of the double segmental baffle, right? So as you can see that this is the flow configuration, that this is the single segment of the baffle, right? This is the second segment of the baffle, right? So the one is arranged and attached with the shell side, and one is when one is placed at the center. So the fluid direction would be totally different as compared to the previous one. So similarly, this is known as the double segmental baffle, and similarly we can see that there is the triple segmental baffle, three different kinds of baffle, and if we arrange these three components, we'll have a single, up to some extent a circular baffle. But these are three segmental baffles. The baffles will have three segments, three different kinds of the segments, right? This is the smallest one, which is arranged over here, and these are the two segment baffles which are arranged over here, and these are the two baffles which are arranged at this point, right? As you can see that it has the triple segment baffle has the different flow direction or the flow configuration inside the shell. Similarly, we'll have the no tubes in the window segmental baffle, right? The tubes are arranged at the center, and the side place has no tubes. So that's why there are no holes at this point of the baffle. So this is the baffle which has the no holes. So the flow direction would be just like this one, right? And similarly, the disc and donut baffle, the most important one, the most frequently used, the disc and donut baffle. So this is the disc and this is the donut baffle, and it will have the flow direction just like this one. And the next one is the orifice baffle. We have the baffle and the tubes are basically passed through these holes, and there will be the small clearance between the baffle as well as the tube, so it will create the orifice, so the fluid will pass through this orifice. So this is the tube and this is the orifice, and this is the baffle and this is the tube. So this small clearance will be used to pass through the fluid of the shell side. So this is the rod baffle. This is the configuration of the rod baffle, and for the simple tubes there are different kinds of the rods are arranged at different angles. So the baffles could be arranged with or the tubes could be arranged at different layouts that could be arranged in the rod baffles could be arranged in the square pitch as well as or the square layout as well as in the triangular layout. So as you can see that these are the rods which is basically used to hold the tubes inside the shell. So this configuration of of the tubes, which is basically holded by different rods, right? So the arrangement is known as the square layout of the different rods, and this is the triangular layout of different kinds of rod, which is basically holding the different kinds of the tubes inside the shell. So the most important point for the design of the shell and tube heat exchanger is the allocation of the streams. So we have mostly two streams. One is the hot and the cold stream. The second is known as the hot stream. So a decision must be made as to which fluid will flow through the tubes and which will flow through the shell side. In general, following configuration considerations should apply. The first one is the more seriously fouling fluids flows through the tube side, since the cleaning would be more easier for the tube side. So if the mechanical cleaning is required, so that's why we prefer the fouling fluid. The fluid which will cause more fouling will be placed inside the tube side, in the tube side in the shell and tube heat exchanger. So the high pressure fluid flows through the tube side because of their small diameters, and the nominal thickness of the tubes are available to withstand the higher pressures. So usually the tubes have ability to withstand the higher pressure, so that's why the fluid stream which will have the high pressure will place in the tube sides or the tube channels. Other connections need to be designed to withstand the higher pressure. So the corrosive fluid will be the must flow through the tubes, otherwise both shell and tubes will be corroded. So if the fluid is corrosive, it means that it will cause corrosion. So what will happen? So if we place the corrosive fluid in the shell side, what will happen? The shell side will become corrosive, right? And the outer diameter of the tubes will also be corrosive. So shell and tubes both will be affected. So what we will do is we will place the fluids inside the tube, and the tube materials should be specially designed in order to minimize the corrosion or to resist the corrosion, right? Special alloys should be designed to resist or to minimize the corrosion. So it is much less expensive to provide the special alloy tubes than to provide both special tubes and the special alloy shell. So it is better to use the special alloy tubes rather than we use the special alloy shell and the special alloy tubes if we want to place the corrosive fluid in the shell side. So this is not the recommended practice to use the corrosive fluid in the shell side, because it will affect both shells and tubes. So what we will do is, the ultimate point is, we will select the tubes which has the ability to minimize the corrosion or to resist the corrosion, and we will put the corrosive fluids in the tube side. The streams with the lower heat transfer coefficient flows on the shell side, since it is easy to design the outside fin tubes. In general, it is better to put the streams with the lower mass flow rate on the shell side. So the turbulent flow is obtained at the lower Reynolds number on the shell side. So the 2 or 3 points has been explained in this point, that if the mass flow rate is low, so there are different flow arrangements in the shell side. So there will be the maximum turbulence because of the presence of the baffles. So because of the turbulent flow in the shell side, the maximum heat transfer will be there, and it is easier to design the outer tubes in the shell and tube heat exchanger, right? So if we put the fins on the outer side of the tubes, that will ultimately help to increase the heat transfer coefficient. So problem arises when the above requirements are in conflict. Then the designer at the place which must have to trade off and find the most economical solution for the design of the shell and tube heat exchanger. The next is the basic design procedure, the thermal design procedure of the heat exchanger. So first of all, the next first step is the problem identification, right? So you will have to follow the same procedure or the same strategy in order to design the shell and tube heat exchanger, right? So I will give you one example in the quiz of the shell and tube heat exchanger in the upcoming Wednesday, so that you will get the idea that how to design the shell and tube heat exchanger. First of all, the first step is the design identification, problem identification, and then the selection of the basic heat exchanger type. So you have done these two things. The next is selection of the tentative set of the heat exchanger parameters, and then you have to perform the calculations, rating of the design, thermal performance, and you have to perform the calculations, and you have to determine the pressure drop. And then after determining the pressure drop, you have to evaluate whether it is under the acceptable limit, right? If it is in the acceptable limit, so you will go for the mechanical design and the costing, etc. If it is not in the acceptable limit, what you will have to do is whether it is an acceptable limit or unacceptable limit. If yes, it is an acceptable limit, you will go for the mechanical design and the costing. If not is in the acceptable limit, it means that it is unacceptable. So you will modify the design parameters and perform all the calculations once again to get the desired or the acceptable values of the rate of heat transfer as well as the pressure drop. So the next is the some calculations or some correlations for the determination of the shell side film coefficient. This is one of the famous correlation that is basically used for the determination of the shell side coefficient, that is H0. So if the Reynolds number, this is the Reynolds number, first we have to determine the Reynolds number. If the Reynolds number is in between 2000 to 1 million, so this is mainly in the turbulent region. So this is the expression that is being used for the determination of the shell side film coefficient. So the next is the shell side mass velocity. So the shell side mass velocity is the ratio of the mass flow rate divided by the surface area, right? And the surface area would be determined by the internal diameter and the clearance and the baffle spacing and the pitch multiplied by the conversion factor. So first you have to determine the surface area, right? And then after dividing the mass flow rate with the surface area, you will get the shell side mass velocity. Similarly, the shell side equivalent diameter, that is the 4 times the free area divided by the wetted perimeter, right? And the free area for the shell side is having the formula, that is the pitch square, that is basically this is for the square pitch, right? If the tubes are arranged in the square pitch, you have to use this formula. If the tubes are arranged in the triangular pitch, you have to use this formula, right, in order to use the shell side equivalent diameter, right? So everything is given, so no need to memorize any kind of formula. That you must have idea that the parameter that is being used in this formula. So this is PT, stands for the pitch, and the D naught is the outer diameter of the tubes. So this is the same the slide that I have already shown you earlier, that the pitch is the distance between from one center to another center of the 2 adjacent tubes, and the C is the clearance between the 2 tubes, the distance between or the empty space between the 2 tubes, and it could be either the square pitch or the triangular pitch. So this is basically the example which basically shows you for the determination of the equivalent diameter for the equivalent or the square pitch. So compute the shell side equivalent diameter, for which the outer diameter of the tube is 3 by 4 inches and the 1 inch square pitch, right? So you have to use this formula. So the outer diameter is given, the pitch is also given. This is 1 inch and this is 3 by 4 inch. And after putting the values, you will have it will result the answer in the inches, and you can convert it into feet by divided by 12. So 0.79 feet is the equivalent diameter with of the shell side having the outer diameter of the tube is 3 by 4 and the 1 inch square pitch. So the shell side pressure drop can be determined by using this formula. So the number of crosses can be determined by using this formula, that the tube length divided by the baffle spacing, and this 12 is basically the conversion factor from inch to feet, right? So this is the formula, and after using this, you have to determine the shell side pressure drop. Everything is given that right from here. So this is the friction factor, mass velocity, and the shell side equivalent diameter, and the number of crosses of the shell side, right? And everything is given from here. You have to use this formula for the determination of the shell side pressure drop. So this is a slide which basically shows you the tube side pressure drop. The tube side pressure drop has two different kinds, right? The one is due to the friction of the fluid inside the tubes, right? You have to use this formula. And the one is there must be the pressure drop due to the turn, right? So in most of the cases that where you have to use the U-tube in configuration of the tubes in the shell and tube heat exchanger, there is a turn, special turn, because of the turn, right? Or the fluid, there will be the pressure drop because of the U-turn in the tube side. So this pressure drop is known as the return pressure drop. So it is basically determined by using this formula. So ultimately the tube side pressure drop can be determined by using this formula, in which we have to take the summation of the tube side pressure drop because of the friction and the return pressure drop. After taking the sum of these two pressure drop, you will have the total pressure drop in the tube side. Now let's talk about the design steps of the shell and tube heat exchanger. And after having a look on the different design steps, I will go through a design problem for the shell and tube heat exchanger 1-2 shell and tube heat exchanger. So 1 shell and 2 tube passes shell and tube heat exchanger design. So the design steps are almost similar that you have already been studied for the design of the double pipe heat exchanger. So there will be the little bit modifications. So let me just go through the calculation of an existing 1 tube heat exchanger. Process conditions are required. So the hot fluid would represent by the capital T1 and capital T2 mass flow rate, and the specific heat and the specific gravity, viscosity, thermal conductivity, and the dirt factor, as well as the pressure drop. Similarly for the cold fluid. So for the shell side, you will need to have the internal diameter and the baffle spaces and the baffle passes, the shell passes. And for the tube side, you will have to know that about the number of the tubes and the length of the tubes and the outer diameter, the ring or wire gauge. And this is basically the standard for the different kinds of the tubes that you will use, and the tube pitch and the number of passes. So this information that you have to you will need for the design of the double pipe the shell and tube heat exchanger. So the first step is the heat balance, and the second one is the true temperature difference, and then there will be you have to use the two different pressure ratios, temperature ratios, and then you have to determine the LMTD. And LMTD, there will be some correction factor for the determination of the true temperature difference. So then there will be the caloric temperature for the hot stream as well as the cold stream, and after that you will have to allocate the hot side fluid and the cold side fluid for either for the shell side or the tube side, depending upon the design steps or the number of points that have already been discussed for the allocation of the stream. And then for the shell side and the tube side, almost all the points are similar. You have to determine the flow area and the mass velocity, and then you have to determine the Reynolds number. The 7th point is you have to determine the Cold burn factor JH from the graph, which is given in the 24 figure, and then you have to determine different parameters like specific heat and thermal conductivity, and then you have to determine finally the film side coefficient for the shell side as well as the tube side. And then there will be some determination of the tube wall temperature, and this is the particular expression will be given. I will explain it in the design problem, so that how can you use it, how you will use it. And then you will have to determine this ratio, this phi s, which is the viscosity correction factor. So in the previous slide we have taken this point is equal to 1, right? But this, for this you have to determine the viscosity correction parameter, right? If the viscosity changes over the temperature range is very small, you can take it as 1. If there will be major viscosity change, you have to use this correction factor, and there will be some correction. Then the next step is you have to determine the corrected coefficient for the shell side as well as the tube side, depending upon this viscosity correction parameter. and then you have to determine the clean overall coefficient, design overall coefficient, and then ultimately you have to determine the the surface area, the heat transfer surface area, depending upon this clean overall and the design overall coefficient, and ultimately you have to determine the dirt factor. And finally, you have to perform the calculations for the tube side pressure drop as well as the shell side pressure drop. As you have already know that for the shell side pressure drop you have to use this formula, and the tube side you have to use two different formulas. For the one accounts for the friction of the fluid inside the tubes, and the second one is known as the return pressure drop because of the presence of the bends and joints and the tube sides. So ultimately, for the total pressure drop in the tube side, you will have to add all the pressures that you will get the total pressure drop at the end. Let's have a look on the design problem of the shell and tube heat exchanger. So this is an example of 7.3 that is from the book of the process heat transfer by D.Q. Kern. So you need to perform the calculations for the kerosene crude oil exchanger. So here it is, even let me just read the question statement. That is 43,800 pound per hour of the kerosene oil with the specific gravity of 42 degree API leaves the bottom of the distillation column at the temperature of 390 Fahrenheit and will be cooled to 200 degree Fahrenheit. So this is the hot stream. So this is the hot stream, and it should be cooled down. So by another stream, which is known as the mid-continent crude oil, having a mass flow rate of 149,000 pound per hour with the specific gravity of 34 API, and it is coming from the storage at the temperature of 100 degree Fahrenheit, and after taking the heat from the hot stream, its temperature will rise to 170 degree Fahrenheit. So the pressure drop must be less than 10 psi, and the combined dirt factor would not be greater than 0.003, and the available for this service is the 21 into 1/4 inch internal diameter exchanger having 158 1-inch outer diameter tubes. These are the number of tubes, and the 13 Birmingham wire gauge tubes with the 16 feet long. And this is the dimensions, and laid out with the square pitch 1 into 1/4 inch square pitch. So the pitch that is represented by PT is 1 into 1/4 inch, and the bundle is arranged for 4 passes, and the baffles are spaced with the 5 inch apart. So the baffle spacing, which is represented by B, is given as 5 inches. So will the exchanger is suitable? You have to evaluate whether this exchanger is suitable or not, and what is the required dirt factor. Let me just go to the solution of the heat exchanger design. So the parameters which are given for the shell side, the internal diameter and the baffle spaces and the number of passes. Similarly for the tube passes, which is the number of tubes and the length of the tubes, internal outer diameter, Birmingham wire gauge, and the pitch and the number of passes. So the shell side configuration and the tube side configuration, this is given in the question statement. So first you need to perform the heat balance, and after performing the heat balance you will get that the rate of heat transfer for the hot and the cold stream both are seen. So it means that the amount of heat which is basically released by the hot stream is equal to the amount of heat which is basically absorbed by the cold stream. So these are the mass flow rates which are given, and the temperatures are also given. The 4 temperatures are also given. The specific heat can be taken from the appendix. And how can we take the specific heat for different fluids? I have already explained in one of the previous example of the design of the double pipe heat exchanger. So the next step is to determine the true temperature difference. First you need to perform to write down the hot fluid temperature and the cold fluid temperature difference and the temperature differences. Then you need to perform you need to put the values in the temperature ratios, that is R and S, and then perform the calculations for. Then you have to perform the calculations for the LMTD, assuming the counter current flow, and then from the figure 18, by using the values of R and S, you can determine the correction factor FT, and you have to multiply the correction factor with the LMTD value, and this will be the true temperature difference, which is 138 degree Fahrenheit for this case. The next is you have to determine the caloric temperature for the hot fluid as well as the cold fluid, because these temperatures will be used to determine the fluid properties such as viscosity, thermal conductivity, and other properties as well. So the formula is also given by using the figure 17. You can easily calculate the caloric temperature for the hot fluid, which is 280, and for the caloric temperature for the cold fluid, which is 129 degree Fahrenheit. Since the flow area for both the shell and tubes are similar, nearly equal, assume that the larger stream will flow into the tubes and start the calculation on the tube side. So the kerosene will take on the shell side and the crude oil will take it on the tube side, because the crude oil has the higher mass flow rate, and the mass flow rate for the crude oil, which is equivalent to 149,000, right, which is given in the question statement. So you need to perform the calculation for the flow area, and the formula has already been explained that for the shell side the flow area would be this. There is a little correction that previously I have said that this is the surface area, but this should be the flow area. So this is a little bit confusion. There is a little bit confusion that I want to correct it, that this AS previously that is being used for the surface area, but here it is the flow area. In one of the previous slide I have mentioned this is the surface area, but no, this is the flow area for the shell side as well as for the tube side. So after putting the values, internal diameter is also given, C is the clearance is also given, and you can either take it from one of the tables, that is that you can take it from the given dimensions of the shell side, and the baffle spacing is also given, pitch side is also given, and after putting the value you will have the flow area for the shell side. Similarly, the number of tubes and the flow area you can take it from the table for the tube side in the table 10, and by using the Birmingham wire gauge and the other specification for the tube side, and after putting all the values in this formula you will get the values for the flow area of the tube side. And then the number 5th point is you have to determine the mass velocity for the shell side as well as the mass velocity for the tube side. And how you can determine the mass velocity for the shell side and the tube side, what you have to do is you have to divide the mass flow rate with the flow area for the shell side and the mass flow rate and divided by the flow area of the tube side. You will get the mass velocity to 97,000 pound per hour per feet square, that is for the shell side mass velocity, and 1060000 pound per hour per feet square is the mass velocity for the tube side. The next is you have to determine the Reynolds number. The Reynolds number, you need to get the value of the equivalent diameter and the mass velocity and the viscosity, and these values should be determined at the given temperature, that is for the caloric temperature for the shell side as well as the tube side, right? And you need to determine the Reynolds number in the point 6, and this point is similar to the point explained in one of the design step of the double pipe heat exchanger. And from the Reynolds number you have to determine the JH factor from the figure 28. This is same for the shell side and the same step for the tube side, right? But for the figure number 18 that is being used for the determination of the JH factor using this Reynolds number value 25,300 for the determination of JH factor for the shell side, and the Reynolds number for the tube side is very small, right, compared to the shell side. So 822 220, and from the figure 24 you can get the value of the JH Goldman factor for the tube side, that will be equal to 31. And then the next step is at the caloric temperature for the shell side as well as the tube side, you have to determine the parameter, that is the specific heat and the conductivity and other parameters. And then you have to determine the film coefficient for the shell side as well as the tube side, and the parameters are also given by putting the values of all the parameters, that is the JH that you have already determined, the thermal conductivity, equivalent diameter, and this parameter as well. So after that you will get the value of the film coefficient for the shell side as the tube side, right? Here you don't have the value for the viscosity correction parameter, right, phi s. So what you will do is you will divide it over here by the shell side film coefficient, right, and similarly for the tube side film coefficient. And then you have to determine the tube wall temperature. Tube wall temperature you can determine using this formula, right? After putting the values, you will get the value of tube wall temperature is this one, and from the tube wall temperature for the shell side as well as for the tube side, you can get the value of viscosity correction parameter, right, for the tube side as well as the shell side. And then you have to determine the corrected values for the tube side as well as the shell side film coefficients after putting the values of viscosity correction parameter. And ultimately for the shell side it will be equal to 162, and for the tube side it will be equal to 121 BTU per hour per foot square per degree Fahrenheit. And then the steps are almost same that you have already performed, that determine the clean overall coefficient and the design overall coefficient as well as the total surface area. And then you have to compare that whether it is in between in the required limit or not. So you have calculated that the dirt factor is 0.00348, but the required is 0.300. It is nearly equal, right? Then you have to perform the calculations for the pressure drop for the shell side as well as for the tube side. So after putting the values in the formulas for the pressure drop for the shell side as well as in the tube side, you will get the value of the pressure drop in the shell side that will be equal to 3.5 psi, as well as the total pressure drop in the tube side. The one is for the pressure drop due to the friction, and this is the pressure drop that is 2.9, that is because of the bends, or and this is known as the return pressure drop. And after adding 6.3 that is here due to the friction, and 2.9 that is for the bends or the return pressure drop, overall the pressure drop in the tube side that is 9.2, and the allowable limit is 10. So both the pressure drops are in the allowable limit, so you can proceed further. It has been seen that the dirt factor that you have calculated is 0.00348 will be obtained, although only 0.003 will be required to provide the reasonable maintenance period. The pressure drops have not been exceeded, and the exceedure will be satisfactory for the surface. And with this is the end of the lecture. I hope the students will go through this example properly, so that you will get the similar kind of problem in the exam. Then that will be the C5 level problem that you will have to evaluate whether this exchanger is suitable for the particular service or not. With this, I will end the lecture.